Hello. Is there anything you want to ask me? Hello, am I audible? Hello. Hello. Well, I don't see any problem with my microphone, so I should be audible. If I am not audible, please say so in the chat. Otherwise, I'll start the session. Welcome to the first problem solving session on digital electronics. I am Sachin Sampath, a PhD student, PMRF student in IAC EC department. And today's topic will be number systems. So the style of these sessions will be that I will first revise through the topic, the theory of the topic, and then we'll solve a few problems and we'll continue that. Recorded lectures will be made available for the people who are unable to attend the live session. If you have any doubts, then you can attend the lecture next week and get it clarified. Alright, we'll start with the content. So we are going to look at number systems today. We already know decimal number system where the base of the system or the radix is 10. And what that means is that there are 10 different symbols and each of them represents a different quantity from 0 to 10. And when you write out a number in the decimal system, the place value of each of the digits is a power of 10. So that's why it's called the decimal system. Deci is 10. So if you have some number d2, d1, d0 point, and the point tells you the what is the weight by which you multiply the digits, that it kind of tells you what place which digit is. So if you have a number d2, d1, d0 point, d minus 1, d minus 2, etc., then the actual value of that number would be d0 times 10 power 0 plus d1 times 10 power 1 plus d2 times 10 square, which is 100, plus d minus 1 times 10 power minus 1, etc. So this is how you represent a number in the decimal system. For example, the number 101.11 in decimal system will be 1 times 100 plus 0 times a 10 plus 1 times a 1 plus 1 times zero point 0.1 plus 1 times 0.01. But this decimal system is useful for humans to interact with each other, but it's not amenable to use in a computer. In a computer, the thing that the computer will understand is binary numbers, and this is because most of the storage, representation, arithmetic is all done using transistors, which can act as switches. So a switch can have two states, right? A light switch, say, it can either be on or off. So there are two states for the switch, and each of them you can take to represent one particular number. It can be a 0 if it's off, a 1 if it's on, or if you are using active low logic, it could be a 0 if it's high or a 1 if it's low. So there are only two levels that a transistor can show, so we use one digit for each of those levels. That's why all your computers and electronic equipment will use binary number system. And in binary number system, there are two digits, 0 and 1. And similar, it's exactly the same as the decimal number system, except that wherever there's a 10, you replace it with a 2. So if you have a number b2, b1, b0, point, b minus 1, b minus 2, each of that digit is multiplied by a power of 2. So b0 gets multiplied by 2 power 0, b1 gets multiplied by 2 power 1, and the way you decide which digit is b0 is through the decimal point. The number to the left of the decimal point, immediately to the left, is b0, and the number immediately to the right is b minus 1. And so these are the weights in a binary number system. So 2 power 0, 2 power 1, 2 square, and to the right of the decimal point it will go as 2 power minus 1, 2 power minus 2. So for the same number which we had written in decimal 101.11, in binary it would have a different value. As you can see, 101.11 is 1 times 2 square, which is 4, plus 0 times 2 power 1, 0, plus 1 times 2 power 0, which is 1, plus 1 times 2 power minus 1, plus 1 times 2 power minus 2, which is 4 plus 1 plus 0.5 plus 0.25. So it's 5.75 in decimal. So it's not the same as 101.11 in decimal. Alright, a few terms you need to know in binary systems is if you have 8 bits or 8 digits, that's called 1 byte. And 2 power 10 is called a kilo, represented with a capital K. 2 power 20 is called a mega, represented with a capital M. 2 power 30 is 1 giga, represented with capital G. And 2 power 40 is 1 tera, represented with capital T. We have two more systems that are useful in different areas. Octal system, sometimes they use in aerospace. Hexadecimal system, you use it to represent memories, especially when you are writing code in assembly language or lower level language, or if you are writing some address information in a manual, instruction manual, say for some device, then writing a large number of binary digits is a waste of space and it's difficult to understand for us humans. So during those times we use hexadecimal system. And in the octal system there are 8 symbols, 0 to 7, 8 is not included. And again, the same number in octal would have powers of 8 multiplying it. So the weights are 8 power 0, 8 power 8 square to the left of the decimal point, and to the right it's 8 power minus 1, 8 power minus 2, etc. So the same number 101.11 in base 8 would come out to be 64 plus 1 plus 0.125 plus just the number that I've written there. Similarly, in hexadecimal system, we have 16 different symbols. 0 to 9 we borrow from the decimal system. From 10 to 15 we use alphabets. This is common practice for any number system where the number of digits exceeds 10. So you need a number more than 9, then you use letters of the alphabet. And similarly, say you have some number a01.bc, That's value would be in decimal. A is 10, 10 times 16 square. So this is the 16. So if you remember in your decimal system, you would write this as the hundreds place, the tens place, the units place, and this is the tenths place, etc. So similarly here, this is the 16s place, this is the 16 squares place, this is 16, this is ones place, this is 1 over 16's place, this is 1 over 256, that's 16 squares place. So, and you multiply with the corresponding digits that you have. A is 10, so it's 10 times 16 square plus 0 times 16, etc. And you find that to be equivalent to this number. So the same number, to represent the same number in different number systems, you'll have different symbols used, and two different such representations will be said to be equivalent if they turn out to have the same value in decimal. And we would like to convert these hexadecimal numbers to octal to binary. So all these conversions are useful. So we'll look at a few conversions. We already saw how to convert any of these numbers to decimal form. We just multiply by the weights. Now from decimal to any base r. So this is the principle followed in general. You take the integer part and you divide that by the base or radix. It's also called radix, so they use the symbol r. So the radix in hexadecimal is 16, octal it's 8, decimal 10, and binary 2. You divide the number which is in decimal by r, take note of the remainder, then whatever is left you divide that again by r, write down the remainder, and keep continuing until you are left with a 0. And in the fractional part, instead of dividing, you multiply by r and keep accumulating the integer part of the multiplication. So you have, for example, 1384.16 to base 16. If you want to convert it, yeah, you are converting it to base 16, so you have to divide by 16. You take the integer part 1384, divide by 16, you will get 16 into 86 plus 8, so the quotient is 86, remainder is 8. Then divide that quotient 86 by 16 again. 16 5s are 80, so the remainder is 6. Divide 5 by 16 again, so your 16 goes into 5 0 times and remainder is 5. And you write down the remainder in bottom to top order like this: 5 6 8. And for the fractional part, you multiply by 16. 0.16 into 16 is 2.56, and you keep only the integer part separately, that is 2. Then you take the remaining decimal part 0.56, multiply that by 16 again, you'll get 8.96. So you keep the 8, again multiply the decimal part 0.96 by 16. So you continue this process. Sometimes this process will stop. If you get a 0.00, the process will stop. Otherwise it might repeat. Here it's repeating after these numbers 28F5C, those will repeat again. Okay, so that's the basic idea to convert any decimal number to a number in base r. This works for all bases base r. Now the remaining conversions that we have to look at are from octal and hexadecimal to binary, and that is very simple. In an octal number, you represent each of the octal numbers, you convert it into a 3-bit binary number, and in hexadecimal each of the digits you convert it into a 4-bit binary number. And you can see that in the example, 5 in binary is 101, 1 in binary is 001, this 2 in binary is 010, 7 is 111, 3 is 011. So you write the 3-bit representations of it. In hexadecimal, similarly, 1 is 0001, 6 is 0110, 3 is 0011, 5 is 0101. So that's octal and hexadecimal to binary. If you want to convert from binary to octal and hexadecimal, you carry out the reverse process. So for the integer part, go from right to left. So here I have written a binary number. If you want to convert it into octal, after the integer part, here you have the decimal point or the radix point. So you group 3 bits at a time. So 011, I have grouped this. 011, that's 3 bits. 101, that's 3 bits. Next you have only 2 bits 01. You can add as many zeros as you want to the left of a number in the integer part, so you can change it to 001 and group those 3 bits. And these groups of 3 bits you convert it into its equivalent octal number. So 001 is 1, 101 is 5, 011 is 3. And when you are converting the fractional part, you start grouping from left to right. So you group these 3, then you group these 3. Then in the decimal part, you can add zeros to the end as many as you want. So you can put 2 zeros and group it to form another group. And you write the binary equivalent of that. So 111 is 7, 100 is 4. So that's how you convert a binary number to octal. In hexadecimal, the grouping is done 4 bits at a time. So the same number, if you want to group it into 4 bits, here again you'll have to add a 0 at the end to make a group of 4. It will result in this hexadecimal number. And this thing works with other bases also. It's nothing special with binary, octal and hexadecimal. For example, if you take a base 3 number and you take base 3 squared, so a power of that base 3. Here you had binary to octal. Octal is 8, which is 2 cube. Hexadecimal is 16, which is 2 power 4. So it's a power of 2. Here I have 3 and a power of 3, which is 9. So a number, let's say 2012, this, what is its value? If it's in base 3, the weights are 3 power 0 1, 3 power 1 is 3, 3 square is 9, 3 cubed is 27. So it's 2 times 27, 54, plus 0 plus 3 times 1, 3, plus 1 times 2 is 2. So it's the number 59 base 10. And you do the grouping similar to your octal and hexadecimal. The how many digits you have to group, that depends on the power to which you have raised your original base. So here binary had 2, octal was 2 cube, right? So this power, every 3 bits in octal are binary are equivalent to 1 digit in octal. Here for hexadecimal it's 2 power 4, 16. So every 4 bits in binary would be equivalent to 1 digit in hexadecimal. So here for base 9, which is 3 squared, every 2 digits will be equivalent. So we group 2 digits at a time. So 1 2 you group it, 2 0 you group it. 1 2 is 3 plus 2, which is 5. 2 0 is 2 into 3, plus 0 into 1, which is 6. So 6 5, and then you verify that this is actually working, and to do that you have to multiply by the weights in base 9. So the weights are 1 and 9. 9 times 6 is 54, 1 times 5 is 5. So it works. So it's nothing special with the base. If you have some base and you have another base which is a power of the original base, then whatever the power is, that many bits can be grouped together in this way. So if you want to convert from base 9 to base 3, you do just the reverse. You express each of the base 9 digit using only two base 3 digits. Alright. Next, doing arithmetic operations in these number systems, you can always convert your numbers from whatever system it is to decimal and then do the arithmetic operations. That will lead to lesser number of mistakes when you are doing it by hand, but it will also have more steps because you have to convert it into decimal, right? But all the arithmetic operations happen in the same way in other number systems also. You just have to remember a few things, and I'll show that with examples. So in the decimal system, if you add two numbers 16 and 25, you add the digits in the units place. 6 plus 5 is 11. That is more than 10. So how much will be left over if you subtract a multiple of 10? Just a 1 is left over. So this 11 can be written as a 10 plus a 1, and this 10 is just a 1 in the tens place. So if you have a 1 in the tens place, that's 1 10. 1 in the units place, that's 1 1. That will become 11. So that is carried over, right? You carry over a 10, which is a 1 in the tens place. So 1 plus 2, that will be 4. So you'll get 41. That's how you do in normal decimal. That is very simple. You already know that. Suppose you want to do the same thing in hexadecimal. You have two numbers, A2 base 16 and DB base 16. Now let's do the same operation. 2 plus B. B is 11, and 11 plus 2 is 13, which is D in hexadecimal. Okay, you get D. And A plus D. A plus D is 10 plus 13. That's 23. But what is 23? You remove a multiple of 16. So you can write 23 as 16 plus 7. And the 16, a group of 16 can be carried over to the next place. So that 16 is carried over as a 1 to the next place, and leftover 7 is written in that 16th place. Okay, so here whenever you exceeded 10, when you got something that was a something above 10, then you subtracted 10 and wrote that down, and that 10 you carried over to the next place. In hexadecimal, if the addition of two digits exceeds 16, the amount by which it exceeds 16, you write it down in that particular place itself and carry over a 1 to the next place. In octal, if two digits add to more than 8, you do the same thing. You carry over a 1, subtract 8 from the result, write it in that place. Okay, similarly, subtraction, 25 minus 16, so 5 is less than 6. So from the 2, you borrow a 1. That is, you're actually writing this 20 that you have here from 25, you're writing it as two tens, which is 110 plus 10 ones. So the 110 you leave it as it is. The 10 ones are carried over to here. So it's actually 10 plus 5. So you have 15 ones, out of which you are subtracting 6 ones. So you get 9 ones. The same principle is you applied in other number systems also. If you have 72 in octal number system and you subtract 16 in octal number system, 2 is less than 6, so you can't subtract 6 from 2 directly, you have to borrow. So you have 7 eighths, right? It's a eighths place. Out of that, you keep 6 eighths as is and you borrow 1 8. So 1 8 plus 2 is just 10. So from 10 you subtract the 6, you get 4. 6 minus 1 is 5. It's 54 base 8. And you can verify that 72 base 8 is nothing but 58. 16 base 8 is nothing but 14 base 10. If you subtract, you have to get 44, which is exactly this. 5 into 8, 40 plus 4, it's 44. The same thing with multiplication also. In multiplication, first you take the units place of the bottom number and multiply that with the top number. So it's 25 times 6, 150. Then you write a 0, so you're shifting by one place, and you multiply your 1 by your top number, that's 25. You write that down and add those two numbers, and you will get the result. The same thing is done in other number systems also. I am using the same numbers from the previous example, 58 and 14, written down in octal. So 6 times 72. How do you do that? 6 times 2 is 12. That exceeds 8 by 4. So in octal, a 12 is nothing but 1 4. So 4 and that 1 is carried over. 6 times 7 is 42 plus 1 is 43. A 43 in octal is what? So 8 goes 5 times. So 43 can be written as 40 plus 3, which is nothing but 5 into 8 plus 3. So 43 in octal is 5 3. So you write down 5 3. And then again you leave a space, you shift by one place, you write a 0 there, you multiply 72 by 1, that will give you 72, and then you add. So you'll get a 4, 3 plus 2 is 5, 5 plus 7, it's a 12 in decimal, but in octal you subtract 8, you'll get a 4, and that remaining 1 you carry it over, so it's 1454. The same way you can do division also. You can check that yourself, you'll get the same result. Okay, next thing we'll see in numbers is the complement of a number. There are two types of complements. Again, this applies in general to every number system, it's not just binary. If the base or radix is r, the diminished radix complement or the r minus 1's complement is this number, r power n minus 1 minus capital N. So in effect, what is it? In binary, that will become flipping the bits. It's the ones complement. In some other number system, say suppose in the decimal system, the r minus 1 or the 9's complement is 10 cube minus 1 minus 512. 10 cube minus 1 will be 999. So 999 minus 512, which is 487. So from the radix minus 1, or that is 10 minus 1, which is 9, you subtract each of the digits. So 9 minus 5 is 4, 9 minus 1 is 8, 9 minus 2 is 7. That's a easy way to do r minus 1's complement. So 1's complement, the same thing. Here the radix is 2 and there are 3 digits. So 2 cube minus 1 minus 101. 2 cube minus 1 is 7, which is 111, minus 101 is 010. Right, the principle is the same. We just use one's binary system more often, that's all. And then we have the radix complement, which is the r's complement. In binary it's the 2's complement. which is nothing but if there are n digits in your number in base r and capital N is your number, it's r power n minus capital N. And you can add and subtract a 1 to write it as r power n minus 1 minus capital N plus 1. So this quantity is your r minus 1's complement. So you're adding a 1 to that. This is for numbers not equal to 0. For the number 0, the 2's complement is 0 itself. Alright. So we have seen this in binary, the 2's complement 101. You flip the bits, you'll get 010 and you add a 1. So it's 011. So in some other systems, as say decimal system, you don't flip the bits, but you subtract each digit from 9. So it's 4, 8, 7, and you add a 1. You get 488. So you will usually do subtraction with 2's complement or the r's complement. The same thing can be done for other base numbers also. What we usually see is doing subtraction with 2's complement, but it can be done similarly in other number systems also. What you do is, if you want to find m minus n, you write capital N in the r's complement form. So r's complement of capital N is r power n minus capital N, and you add it to your minuend. So it will become m plus r power n minus n, which is capital M minus capital N plus r power n. So in case m is greater than or equal to n, then this r power n will appear as a carry, and you just discard the carry, and what you get as a result is m minus n. This carry will appear in the uh, n plus 1th bit, so you can easily discard that. It won't affect the rest of the result. But in case m is the smaller number and your result is negative, then this m minus n plus r power n can be written as r power n minus m minus n. So it's the r's complement of m minus n. So you already get it in the negative form. So if you take the r's complement of this number again, you will get the magnitude of m minus n. So that's performing subtraction using complement. So when we saw the complement form, and that is useful when representing numbers. So we have seen unsigned numbers. In decimal, we have seen positive and negative numbers. While writing, we write a plus sign and a minus sign, but a computer you can't store that, right? You can store only bits. So to say that a number is positive or negative, one method is using sign magnitude, where one bit is dedicated, the MSB is dedicated to indicate the sign. If that is a 1, it's a negative number. If the MSB is a 0, it's a positive number. So if you have the bit pattern 11001, and if it's unsigned, you multiply by weights 1, 2, 4, 8, 16, and you'll get the number 25. But if you have it in the signed magnitude form, then the MSB is a signed bit. So since it is 1, this number is actually minus 9. For positive numbers, the signed bit will be 0. Another representation is signed complement representation, where to represent the negative of some number, say minus 9, you write out 9 and take its 2's complement. Whatever you get, you say that is. See, at the end of the day, all these things are just bits stored in some pattern in your computer. How you interpret those are left up to you. How you use those in arithmetic, everything is up to you. So I can say that if I have a number, say 9, I will take its 2's complement and I will say that is the negative of that number. So minus 9 is represented with 2's complement of 9. Okay. Okay, when you are adding or subtracting numbers represented using signed complement form, when we are adding, we just take the numbers. If both the numbers are in two's complement form, we add them. If there is a carry, we just discard it. When we want to subtract one number from the other, we take the two's complement of the subtrahend and again add that to the minuend, and if there's a carry, we discard it. So you see that both addition and subtraction can be done by using addition itself. So if you want to make a circuit, which we'll see later, you can use the same circuit with just a little bit of additional circuitry. So you can do two operations using almost the same circuit. That's why everywhere use only two's complement representation to represent numbers. And one thing you have to make sure is, if you have a limited number of bits available, when you are performing addition or subtraction, should make sure that the result of your addition or subtraction is not out of the range of your number representation. So if you have 7 bits, you can have 2 power 7, that is 128 different numbers. If you are using a signed number format, half of these numbers, say 64 numbers, including 0 and positive numbers, will be positive, and the other half will be negative numbers. So you will only be able to represent up to from minus 64 to plus 63. So there's a 0 included. So it's 128 numbers. And if you add two numbers like 60 and 60, the result is 120, which cannot be represented with 7 bits because 63 is the limit. So you have to make sure that such a situation doesn't happen. You'll have to allocate more bits. Okay. So we have looked at the theory behind all this. We'll do a few problems to hammer home the concept. Okay. Give me a minute. So some of these problems are straightforward, just computation, and some of these problems are just a little bit different. But in number systems, there's nothing too complicated. Okay, we'll start out with a very simple one. Using capital A and capital B for the last two digits, list the numbers from 8 to 25 in base 12. Alright, so base 12, there are 12 digits. It starts from 0, you go up to 9, and then for 10 you use A, for 11 you use B. And let's make a table decimal in base 12. So 8 will be the same in both, 9 will be 9, 10 will be A in base 12, 11 will be B, 12 will be 1 0. So in base 12 the weights are 1 and 12. So it's 1 times 12 plus 0 times 1. It's 1 0. Again 13 will be 1 1, 14 1 2. This kind of change you would have seen in your car or vehicle's odometer, where the number of kilometers are counted. So the LSB will be incremented by 1, say for every 100 meters or for every meter or what. And then once that reaches 9, it will be reset to 0, and then the next bit will start counting up. It will go 2 2 3 2. Once it goes to 2, again the first bit will start counting up 1 2 3. It will go to 9, and then once it crosses 9, it will go to 0 again. It will be reset. This 2 will become a 3. So that's the same procedure we follow. So 14 is 1 2, 15 is 1 3, 14, 15, 16, 17, 18, 19, 22. What will 22 be? No, see, it's base 12, so there are two more symbols left. It will be 1A. It can go up to, it's a base 12 system, right? It can go up to 11. So 23 will be 1B. Now 24, now more than B, you have to increase B by 1. That will be a 12, but you don't have a symbol for 12. So this is the 12th place. So that will change to 20. And they've asked, okay, 25 will just be 21 and it will go on. So that's the way these numbers go. Alright. Convert the following numbers to decimal. Very simple. Base 5, the weights will be 1, 5, 5 square which is 25, 5 cubed which is 125. So 4 times 125 is 500 plus 3 times 25 is 75. 5 times 1 is 5 plus 0 which will be 580 in base 10. Similarly, 198 base 12, the weights in base 12 will be 1, 12, 144, have 198, it will be 144 plus 108 plus 8, which is 216 base 10. So the conversions work that way. That's some drill on conversions. Alright. Next question. What is the largest binary number that can be expressed with n bits? What are the equivalent decimal and hexadecimal numbers for n is equal to 16? So the largest number you can have is just a number with all ones. So there are n digits. So there will be n ones. As the maximum value can represent in binary. And these are multiplied by their weights. 1, 2, 2 power n minus 2 up to 2 power n minus 1. So the value of this number will be nothing but 1 plus 2 plus 2 square etc. up to 2 power n minus 1. You can observe this is a geometric series with first term a is 1, common ratio r is 2, and there are n terms. So the sum of the geometric series is a into 1 minus r power n by 1 minus r. Substituting the values, you will get 1 into 1 minus 2 power n by 1 minus 2, which is nothing but 2 power n minus 1. Or you could, one more way to think of it is, if this is the maximum number, just one number more than this will be, if you add a 1 to this, you'll get 1 plus 1 0, 1 will be carried over, 1 plus 1 0, 1 will be carried over, and it will keep carrying over and over again until you get the number 1 followed by n zeros, and this will have a value of a weight of 2 power n. So 1 more than this number is 2 power n, so this number will be 2 power n minus 1. That's another way to think about it. Right? For n is equal to 16, the decimal equivalent is 2 power 16 minus 1, which will be 65,536 minus 1, which will be 65535. Same number if you want to write in hexadecimal, you group 4 bits at a time. Since there are 16 bits, there are 4 groups of 4. So the number is FFFF in base 16. So here you can see from the example, as we increase the base, the number of digits we need to represent will decrease. So in base 10 we needed 5 digits. In base 16 we needed only 4. In base 2 we needed 16 digits to represent the same exact number. So while we are talking to other humans, or if you are writing an instruction manual, or if you are writing some assembly program, it is more convenient to use hexadecimal because it will occupy less space and it's easier to type out. Okay, and large values can be represented with very few bits. So memories, there will be tons of memory, and if you want to write down the memory addresses for somewhere for human use, of course the computer will only see binary, but if some human wants to know the memory address, it's very convenient to write down in hexadecimal. Okay, next question: determine the base of the numbers in each case for the following operations to be correct. So 14 by 2 is 5. That means if it's base b, b plus 4 by 2 is 5. So b plus 4 is 10, b is 6. That is in base 6. 54 by 4 is equal to 13, then 5b plus 4 by 4 is 13. So 5b plus 4 is 52. Wait, 13 also has to be written in that form. It's b plus 3. So this is 4b plus 12. So b is 8. And you can check that if it's in base 8, 54 is 5 into 4, 5 into 8, 40 plus 4, which is 44. And 54 by 4 is 44 by 4, which is 11. And 13 base 8 is 8 plus 3, which is 11. So the numbers are in base 8. Similarly, part C, 24 plus 17, 24 is 2b plus 4, 17 is b plus 7, is equal to 40, which is 4b. This will give you b is equal to 11. So the numbers are in base 11. Alright, so everywhere you have to be uh, sure in what base you are working in. For example, in error correcting codes, when you are using binary codes, there's something called a generator matrix to generate the code words. So you have some message, which is a series of bits. You want to convert it into some code word, which is also a series of bits. It's a different series of bits with extra bits added. And that time you do that by multiplying your message bits with a matrix of binary numbers. And some type of matrices have special properties which are very useful. So if you have a k by n matrix, you would like your rank of the matrix to be k if there are k rows. So that's the max rank you can have. And when you're checking for the rank, you do that using, if you learnt in linear algebra, you do that using elimination. You can do that. But while doing elimination, you shouldn't forget that the operations you're doing are in base 2. So all your linear algebra courses will actually be taught in decimal system. And when you try to do operations with a matrix in base 2, you might sometimes forget that fact and you might get a different rank. So the same matrix in different bases will have different ranks. So that's why you should always be careful with what base the number is in. Okay, Next question, the solutions to the quadratic equation x square minus 11x plus 22 is 0 are x is equal to 3 and x is equal to 6. What is the base of the numbers? So a quadratic equation which has solutions a and b is of the form x minus a into x minus b equals 0. Then a and b are solutions. So if you plug in a here, it's a minus a times a minus b, which is 0. So the statement is true. And similarly, if you plug in b, the statement holds. So this is the quadratic equation with roots a and b. And here they have given the roots as 3 and 6. So the quadratic equation is actually x minus 3 into x minus 6 equals 0. It is x square minus 9x plus 18 equals 0. So in base b, it's x square minus 11 base b x plus 22 base b is 0. So 11 base b, which is b plus 1, is equal to 9. 22 in base b, which is 2b plus 2, is 18. You solve this system of equations, you subtract the first equation from the second, you get b plus 1 is 9 or b is 8. So the quadratic equation had coefficients in base 8. Alright. Convert the hexadecimal number 64 CD to binary and then to octal. Let's do that. 64 CD base 16. To convert it to binary, you write each of these digits using 4-bit binary representation. 0110, 0100, 1100, 1101. That's in binary. Now you convert that into octal. You convert it by grouping it into groups of 3. If there's a 0 to the left, you can just ignore it, or you can add 2 more zeros. It will become a group of 0 0 0. So this will be in octal then 0 6 2 3 1 5, which is in I keep writing 7, but it's 8. That's in octal. Alright. Question 7. Convert the following binary numbers to hexadecimal and then decimal. Why is the number b 4 times the number a? So to convert to hexadecimal, we do grouping in groups of 4. So that's one group. Here you can write it out as 0001, but it's not really necessary. Again here you can do the same. So this will be 1.90 in hexadecimal, which is nothing but 1 plus 9 over 16. So 25 over 16 will be 1.5625 in decimal. And the number b 110.010, again you group 4 bits together, which is 6.4, which will be 6 plus 4 over 16 is 100 over 16, which is obviously 4 times 25 over 16. So the second number is 4 times the first number, and that you can see from the fact that the decimal point is shifted 2 times to get the second number. So if you have a binary number and you multiply it by 2, then it will be the same number as the binary point or the decimal point, the binary point, let's say, shifted one place to the right, and if you divide a binary number by 2, the binary point is shifted one place to the left. So here, since to get the second number the binary point has to be shifted twice, it's 4 times the number. Okay, perform the following division in binary. So again, this is just to show you that all these number systems are nothing special. The concept is the main thing that you need to understand. Then performing the computations is simple. So let's do it. 101 goes 1 times into 111. You subtract, you will get 10. You bring down the 0. 100 goes 0 times. 101 goes 0 times into 100. So you write a 0. You bring down the 1. This goes 1 times 101. You subtract it, you will get 100 again. You bring down this 1. Again it's 1 time. Now you put a decimal point, bring down this 0, 100. Once you'll get 101. This will be 11. Bring down this 0, 110. Again 1 times 101. Subtract, you'll get 1. So you keep doing it. This will be going on forever. So that's how you do division in binary directly. Otherwise you could convert it into decimal, do the division, and then convert it back into binary. Okay, add and multiply the following numbers without converting them to decimal. Same principle. 1011 plus 101. 1 plus 1 is 2, which is 10. You would carry a 1. 1 plus 1 is 2. 10, carry a 1. So you'll get this. To multiply this number, again 1 times this number is 1011. 0. 0 times this number is 0000. Shift by 2 places. 1 times this is 1011, and then you add, and you can verify this number is what. This is 8 plus 2 plus 1, 11. This number is 5. 11 times 5, you should get 55. This number 1, 2, 4, 8, 16, 32. This number is 32 plus 16 plus 4 plus 2 plus 1. It's right, correct, right? It's 55. So the same operation in binary. Oh, by the way, these questions are all from a majority of them are from the digital design textbook from Maurice Mano, and some questions are from other courses that I have taught, other NPTEL courses. So, alright, they have asked the same thing in hexadecimal. 2e base 16 plus 34 base 16. E is 14. 14 plus 4 is 18. That will be 1, 2. Carry over the 1. 3 plus 2 plus 1, 6. And you can check that 2e is what number? It's 46. 3, 4 is 52. Sum should be 98. This is 16 times 6, 96, plus 2, it's 98. Alright, and while you do the product, it's the same thing. Should get 46 times 52 is 8 plus 30, 48, 49. 2392, and let's do it in hexadecimal. 4 times c, what is that? 4 into 14, 56. That's 48 plus 8. So it's 8. 48 is 3 times 16. Carry over a 3. 4 into 2 is 8. Plus 3 is 11. 11 is b. 0. So 3 times e is 3 times 14, 52. 52 is no, it's 42. 42 is 32 plus 10. So it's a, and 32 is 2 times 16. So 2 is carried over. 3 2s are 6 plus 2 is 8. 8a is 0. So 8 a plus b is 21, which is 5 with 1 carried over. 8 plus 1 9, 958. You check it. 9 times 256 plus 5 times 16 80 plus 8. So this will be 2304 plus 88, which will be 2392. Okay, that's just more drill. Do the following conversion problems. Calculate the binary equivalent of 2 by 3 out to 8 places, then convert from binary to decimal. How close is the result to 2/3? So, okay, 2/3, right? So it's 3 dividing 2 goes 0 times. What did I do? 0 times, add a 0 once, it's a 1, 0. So it's repeating. 0 times, again you add a 0, 1. So it's repeating. So 2/3 is nothing but 0, 1, 0, 0.10101010, which will turn out to be half 0.5 plus 1/8 0.125 plus 1 over 32 plus 1 over 128. If you do that, you will get something around 0.6640625. And if you did it just in decimal, 2/3 is nothing but 0.666 recurring, right? So there's a difference because you truncated it. In decimal, if you truncate it, you will get something like 0.666. If you truncate it to 7 places, the same result will be 0.66667. If you did do that in binary, it will be 0.6640625. So there are a few errors when you truncate it. So you will have to be careful, right, when you're designing some circuit where division has to be done. You should make sure that this discrepancy doesn't affect your circuit. That's what this question is trying to show. And then you can try it out in hexadecimal. So if you convert this binary number into hexadecimal, then the result won't really change. That's what is there in part B, and you can do that yourself. I mean, if you converted this into hexadecimal, you will get 0.AA base 16, which in the end, when you expand, you will get the same number. So it's not much different. But if you did this division in hexadecimal, right, if then 2/3 would be the same operation as in your decimal. 6 times 18. 18 you might write it in a different way. 1 2, but again it's 2.66. You'll get the same as your decimal. So that's because the 6 exists in your hexadecimal system, so there won't be a problem. So up to base 6, base 7, it's fine. But if you go to base 6 where there are only 5, up to 5, 0, 1, 2, 3, 4, 5, then the result that you get will change depending on how you truncate. Okay. Find the 16th complement of C3DF. So to find the 15th complement, you subtract each of the digits from 16. So you do FFFF minus C3DF, that's 0. 15 minus 13, 2. 15 minus 3, 12C. 15 minus 12, 3. This is the 15th complement. To get the 16th complement, you add 1. So 3C to 1, that's the 16th complement. For the next part, they want us to convert C3DF to binary. That'll be what? C3DF base 16, converting it to binary 1100, because C is 12, 0011, D is 13, 1101, F is 15, 1111. It's in binary. Then they're asking us to find the 2's complement of this binary number. So 1's complement, you just flip the bits, 0011, 1100, 0010, 0000. You add a 1 to get 2's complement, and that is 0011, 1100, 0010, 0001. And in part 4, convert the answer in part C to hexadecimal and compare with the answer in A. So let's first convert it into hexadecimal. That's 3C21 base 16. So you can see that doing the finding the 16th complement in base 16 will give you the same result as finding the 2's complement by converting that number into base 2. And this kind of works out nicely because 16 is a power of 2 itself. So this type of thing should work with other powers of 2 also. It should work with octal. I haven't tried, so you can take that as a homework. Verify in octal or some other number system. So I had shown an example with say we had base 3, base 9. So you can check if this works in those systems also. My intuition is that it should work, but I haven't worked it out myself. Okay. When two n-bit numbers are added, the sum will contain maximum number of dash bits. So maximum value we saw in the previous question. With n bits you can have 2 power n minus 1. So if there are two such numbers, maximum value is sum of that, which is 2 times 2 power n minus 2, 2 power n plus 1 minus 2. This number is less than 2 power n plus 1 minus 1, which is the maximum value that you can represent with n plus 1 bits. So since that is less than that, 2 power n plus 1 minus 2 can also be represented with n plus 1 bits. So a similar type of question was asked in my Qualcomm interview. I think they asked very similar. Maybe it was the same question. So these type of things, even if you don't remember, you should be able to just work it out yourself. All right. If 110 base x is equal to 132 base 4, then what is the value of x? So if it's in base x, the value will be, the place value will be x square x 1, right? So this number will be x square plus x in base 10. 132 base 4, it's in base 4, so it's 16, which is 16 plus 12 plus 2, which is 30. So in decimal, these two numbers are equal. That means their value must be same in decimal number system. If you solve this, you will get 5 or minus 6. You could say x into x plus 1 is 30, 5 into 6 is 30, and minus 6 into minus 5 is 30. But x is a base of our number system. We don't have a negative base number system. So x is 5. Okay. Write the number 225.4375 base 10 in base 4 number system. Convert this number into binary. Okay, writing it in base 4, very easy. You divide by 4, and for the fraction part, you multiply by 12, multiply by 4. So it's 1.75. You take out the 1.75 times 4 is 3.00. Take out the 3. 00 is what? You just stop at that. So 225.4375 in base 10 would be the number. Go in the opposite order here. 3201 point. Go in this order here. 13 base 4. How do you convert it into binary now? So again, if you remember the principle for base 8, which is 2 cubed, we represented each of the octal number using 3 bits. For 2 power 4, which is base 16, we use 4 bits. So what would you do logically for 4, which is 2 square? You will just represent, yeah, you just represent with 2 bits. 3 in 2 bits is 1 1, 2 is 1 0, 0 is 0 0, 1 is 0 1 point, 1 is 0 1 1 1. And you can check this. Let's verify it. You don't want to take my word for it. Uh, yeah, it is. This is the binary equivalent, right? 1 2 4 8 16 32 64 128. This is half, quarter, and eighth, the 16th. So that's 128 plus 64 plus 32. What's that? 128, 188, 192, 222, 224 plus 1 is 225. It will turn out to be, you can do the fractional part also, it will come out as this number. So that's the principle of it. So if you know the principle, you can use it for any number system. Okay. Perform subtraction on the given unsigned numbers using the tens complement of the subtrahend. The result is negative. Find its tens complement. Attach a minus sign and verify. So subtraction using tens complement. So 2579 nines complement. Subtract each digit by 9. 7420. Add a 1. That's your tens complement. So you have to remember, but what you're actually doing is you're doing r power n minus your number, where r is the base, n is the number of digits, minus capital N is this number. So effectively it turns out to be this was r power n minus 1. So that turns out to be the same as subtracting all these digits from 9. So but by definition it's this thing. Okay, it's 7421. Now we add it. We wanted 4637 minus 2579, so you add the tens complement. You get 8 5 12 1. You discard the carry, so 2058, and you can verify 4637 minus 2579, it will be 2058. If you add 2058 to 2579, it will be 2579 plus 2000 will be 4579 plus will be 50 will be 4652 or something. You can do it, and check that you will get the same thing. And what will happen if you have a larger number in you're subtracting a larger number from a smaller number, you will get a negative number. So and the result you get by doing 2's complement subtraction will be in the negative number form. So 1800's 9's complement is 8199. That's correct. Okay, 10's complement, just add 1 to that. You add 1, that will be 8200. So 125 plus 8200 will be 8325. Now this is actually you subtracted a larger number from a smaller number. So what you get is the negative is in tens complement form. It's a negative number. So to check, we will take the tens complement again. 8325. One's complement will be 1674. Two's complement will be 1675. You can check 1675 is plus 125 is 1800. One more thing here is, how do I know in in a binary number system, if there's 1 in the MSB, then it's a negative number in 2's complement form. If there's a 0 in the MSB, then it's a positive number. How do I check that in a decimal number? So the way you think about it is, how many numbers can you represent, say, uh, with uh, with 3 digits in decimal. You have from 000 to 999, that's 1000 patterns, so it can represent 1000 different numbers. If it's unsigned, these 1000 numbers will go from 000 to 999 directly. So there are maximum value you can count is 999. If it's a signed number, you'll have half of this 500 will be negative numbers, 499 will be positive numbers, and 1 will be used for 0 itself. So you can count from minus 500 to 499. So if it's above 499, that is if the hundreds place has a 5 or a number more than 5, then it's a negative number. If it's less than 5, it's a positive number. So that's how you find out if a number is negative or positive in the 2's complement form of a different number system. Okay. Perform subtraction on the given unsigned binary numbers using 2's complement. Verify negative results are in 2's complement form. Same thing we did earlier, except that we will do it with binary numbers because we are more interested in binary. We should have more practice in binary. So let's do it. 10010, 1's complement. This is 9's complement. This is 10's complement. Okay. 1's complement is 01101. 2's complement, you add a 1 to that, you'll get 01110. Then 10011 minus that number will be same as adding its 2's complement. That will give you a 1 carried over, 1 carried over, and then you discard the carry, so it's 1. And you can see that the bit pattern is the same all the way here, except this has a 1 and this has a 0. So subtracting those numbers should have given you a 1. Okay, that's a positive number, no problem. Suppose we are subtracting a larger number, 1101. The 1's complement is 001010. 2's complement is 001011, and you add that to 1001. 1 plus 1 0 with the 1 carried over. 1 plus 1 is 0 with 1 carried over. It will be 010100, and what happened? Okay, so only something. Let me think for a bit. We subtracted a larger number from a smaller number, so the result, okay, we we subtracted a negative number, so the result is in the end is a positive number. So the answer was right. It was 001001 plus 001011 will give you 010100. So this itself is already a negative number, right? So the answer will always, if you subtract a negative number, you'll get a positive positive number. So the answer was right. There is no problem. Okay. Write the 8-bit 2's complement form of minus 45 base 10. Simple, just a drill. 1 2 4 8 16 32. It's 32 plus 8 40 plus 4 plus 1. That's 45. 1's complement 010010. 2's complement 010011. Alright, it's just for practice. Okay, convert decimal plus 49 and plus 29 to binary using signed 2's complement representation and using enough digits to accommodate the numbers. Then perform the binary equivalent of plus 29 plus minus 49, minus 29 plus 49, and minus 29 plus minus 49. Convert the answers back to decimal and verify that they are correct. So here you first convert 49 into binary. 49 is 32 plus 16 plus 1, so you'll have 1. That's 16's place, 32's place. That's in binary. 29 is nothing but 16 plus 8 plus 4 plus 1, which is in binary. Now let's see, we'll use the thing that I told you earlier. How many numbers can you actually have? If you use say 7 bits, then you can go from, there will be 2 power 7 128 representation, so you can go from minus 64 to 63. That's with 7 bits. But while we do operations with 49 and 29, you can get if you add 49 plus 29 directly, you could get 78. So 7 bits won't be enough. That's why we'll have to represent it using 8 bits. So for this number we will have to add 2 more bits, 0011 0001. Here you will have to add 3 more bits, 00011101. So you need 8 bits to make sure that there won't be any overflow. Then we'll take the 2's complement of these numbers, minus 49 base 10, 11001110 plus 1 will be 1. That's the 2's complement. And then minus 29 base 10 will be 11100010 plus 1, that will be 11 in binary. Then when you want to perform these operations, 29 plus minus 49, take 29 and 2's complement representation as this number 29 itself, the unsigned number. minus 49 is 1100 1111, and you add these, one carried over, one carried over. That's your result. We'll do a check. So ones place 2 4 8 16 32 64 128. Okay, this is a negative number, so this is in 2's complement form. You'll have to take the 2's complement again. So 1's complement is 000 10011. 2's complement, you add a 1 to it, 00010. One trick to use is, if there is zeros here, then this number is just 3, right? 011. If you add a 1, you'll get a 4. That's 100. So you don't need to carry over or any do all those operations. You can just write it as 10100. This is nothing but 4 16 20. So minus 49 plus 29 is 20. And we had it in 2's complement negative form, so it was minus 20. Okay, so 2's complement actually works. That's the takeaway. And as long as there's no overflow, you can do subtraction and addition using only addition operation itself. So here this was actually 29 minus 49, but you convert it into an addition problem. Okay, and the other two, minus 29 plus 49 and minus 29 plus minus 49, try it yourself. That'll be homework. So finally, there is some more portion left in when you talk about number systems that you need to know if you want to build circuits using digital electronics, and that is binary codes. I'll in the remaining 15-20 minutes I'll go through the theory of that and the problems, and remain the further portion will start with logic gates, and yeah, mostly logic gates and some combinational circuits in the Saturday's class. So we'll talk for a few minutes about binary codes. Um Even though like our systems and all store information in binary digits, I like I said earlier, what those digits mean is always up to us. So a way to represent code is nothing but assigning a meaning or a mapping from one way of representation to another. So if you have, let's say, some colors and some numbers, so how does the computer understand colors? There's no, it only stores binary digits, right? So, but still, the computer does show colors, pictures, videos, all types of data. So, there must be some type of mapping between your binary patterns and their colors that we do using red, green, and blue. Any color can be represented as a mixture of these colors. There are other color systems also. Uh, I think red, yellow, blue, or something like that. So, and for each of these colors, you kind of give an intensity value. So, how much of red is there, and how much of green is there, how much of blue is there in one particular pixel, let's say. And by mixing those values, those pixels, it will interpret it and show you some type of color. And the intensity of those colors will be stored as some binary values. So there will be kind of a mapping between the binary bit patterns and colors. The same thing happens with other types of data also. So that is what you would call a code. So another type of code would be, like I said, an error correcting code, where you want to remove errors. So sometimes you add extra bits to whatever message you have, and there will always be a one-to-one mapping. So for example, if you have 1011 and you have a space with 7 bits, let's say, that is, you can have numbers like 1010111. So you map this number to this, but in the space of 7 bits you have a lot more numbers. You have 2 power 7 minus 1, or 2 power 7 bit patterns, which is 128 bit patterns. With only 4 of these digits you have 16 bit patterns. So when you map from the 16 pattern space to this 128 pattern space, you are left with a lot of freedom, because you need to select only 16 out of 128, and you can select it in such a way that it is easy for you to recover errors during communication or storage. So that's another type of code. One more type of code you might have seen is ASCII codes to represent letters and symbols. So, letter A, how will the computer store that? It can't store A, right? It will only store digits. So, for certain bit patterns, you can say, okay, these bit patterns will represent that letter A. And what if the same bit patterns have a lesser letter assigned to them and then also a color? That is fine, because when you are reading the file, the software will make sure that if it's an image file, the bit patterns will be interpreted as colors, and if it's a text file, the bit patterns will be converted into letters. So that will be taken care of by the software. So to represent letters, there will be some standard, right? You can't just uh, everybody can't just do their own mappings from the set of bits to the set of letters. So there are different standards. One among them is ASCII, the American Standard Code, something something. I don't remember the abbreviation. And nowadays, it's not just letters. There are emojis, right? Even the emojis are actually bit patterns. So a certain pattern of bits corresponds to a certain type of emoji. So there is a mapping from the group of bits to the image or the emoji there. So that's also a code. So this way, codes are really necessary to work in the real world. Computers will only understand binary, but at the end of the day, the interpretations are left to us. So that's why we need to know a few standard codes that are used for different things. The first thing we'll see is that a binary coded decimal code. So binary coded decimal is very straightforward. Every group of 4 bits represents one decimal symbol. So and the decimal symbol that will correspond to is simply the decimal equivalent of that binary code if you convert it to decimal. So 0000 will represent 0, 0001 will represent 1, 0010, 0011, 0100, 0101, 0110, 0111, that's 7, 8, 9. So there are only 9 up to 9. So there are only 10 digits in decimal system. So you will have only 10 bit patterns. These will correspond to. So the thing you have to understand here is that we are not simply converting this into decimal and saying this number equals 0 in the decimal system. That's not what's happening. We are saying that this particular pattern 0000 represents 0 and this particular pattern 0001 represents 1. So what that means is that, say, if I wanted to, I could say 0001 represents the number 0 and 0000 represents the number 1. Similarly, I can flip the other things also. I can say 0011 represents 2. So it is a kind of mapping that is present here and not an actual arithmetic between these two numbers. So that's why it's a code. Okay, that's the point you have to understand when it comes to BCD. And this is useful because in a lot of applications for humans will only understand decimal systems. So a lot of applications there will only be decimal values. For example, in your calculator, there is a circuit in your calculator that will display things to you, right? That is using a 7-segment display, and that display will only display up to from 0 to 9. So each of those digits will be from 0 to 9. All these other bit patterns with 4 bits, it won't matter to it. So if there's a circuit that converts from, let's say, that takes the value stored in some register, some 4 bits say, and it wants to convert it into a decimal number in a or a binary coded decimal number, and then it will use that to display it in your calculator. So if you had the number 10, say, if you wanted to show it in the calculator, then it would have to store it as 0001 0000. So this is the BCD representation of 10. Okay, so in applications like that, this BCD representation is useful. And then if you want to do arithmetic, 10 plus 21, that will be 13. So this will be stored as 0011 plus 0001. So that's the number 31. But if you converted 31 directly to binary, it would have a different representation, right? It would be 11111. So these two are clearly different. Okay, this is the binary coded decimal representation where each digit in the decimal number is represented using 4 bits in binary. So 10, uh, let's take a bigger number, 56 is represented as 0101 0110. That's the number 56. in BCD. So now you have to take care of arithmetic in BCD. When you're doing BCD addition, you should know when there's a carry and when there's a. So if we add 63 to this, or let me make it so that there are a lot of carries. 74, shall we say? 6 plus 4 is 10, 1 is carried over, 7 plus 5 is 12, 13, 130. So what I want as the result is 0001, 0011, 0000. But suppose I had, that's 56 in BCD, that's 74. You directly added these things, okay? You'll get what? You'll get this number. But that's not the same, right? That's not the result you wanted. So there are certain rules you have to follow when you're doing BCD addition. The way you would do that is each group of 4 bits are added separately. And if the group of 4 bits, when you add them, if it exceeds 10, it has to go to 0, and the however much, if it exceeds 10, it has to go to the number you get by subtracting 10. So if you have 0110 plus 0100 in BCD addition, it should go to 0000 and a carry out of 1. Okay, we'll see later how to build circuits to do this. And then again you'll have 0101, 0111, you add them, that's 12, you had a carry, so that's 13. It should give you 0011 plus a carry out of 1. So that's the type of addition that you want. How to do this we'll see in later classes. So that's binary coded decimal. uh, the remaining part of this I will cover in the next class, and then we'll do some problems, a few problems, not much, and then we'll move on to logic gates in the next class on Saturday. Okay. For people who are watching the recorded lectures later, if you have any doubts with the today's topics, then you can join in the next class and ask me, or you could mail me directly. You know my email ID. So people who are not attending the live lectures, you can email me your doubts. All right. That's it for today's session. See you on Saturday. Bye.